if you guys haven't chatted with me yet, I'm Laura. And we're going to kind of shift gears a little bit today in terms of the invariants we're talking about. So Sebastian's going to introduce symplectic homology and graphic hypothetical.
Yeah. So these objects have been mentioned a few times already, but we'll see more of them today. So the setting is we have some liberal design. We contact boundary and vector C should point out of y, and we use these coordinates. This is r. We attach these keys. X is supposed to be compact. So the first thing one could maybe ask is if you can do Hamiltonian Flirt theory here. So let's take a Hamiltonian. And we'd like to generate a complex on orbits of the Hamiltonian vector field where the differential counts cylinders from one orbit to another. But there's, of course, a non-compactness here, which we have to handle somehow. And one thing that works is if H looks like this. It's something, and then linear with some slope. So H. So then the vector field we're generating on the orbits is just the Reed vector field of y. And as we can choose this at different values, we'll get a different number of Reed orbits. So one, a complex. That's not true. This should be a. So yeah, so the slope matters. And these moduli spaces that we're counting, I'll define them in a second. But do we want to define this? Yeah, so the picture.
What is that condition guarantee?
Pardon?
The C1 effect. What is that guarantee in this context?
Yeah, so the complex will be integrated, but I would like to talk about. Yeah, so the picture is this. You have gamma and this some cylinder to gamma prime. Okay. Goes from gamma and then gamma prime and solves some equation. So, the J's. So if but at the end, the tangent space is essentially it's xi, which is the kernel, the compact distribution. And there's the read, and there's the R. And it's supposed to respect this. So, J on. So I think maybe this has been mentioned that then if you have any of these U's which hit this end, you have a maximum principle. So you always stay on. So if you fix the ends to be gamma and gamma prime, you always stay on this side of gamma and gamma prime.
We always, what's the...
Yeah, so if gamma is maybe here, and gamma prime is maybe here,
Mhm.
all orbits connected then stay like in this region. Assuming if this is the standard.
Oh, yeah.
Okay, that's good. So we can get some compactness. I think that's okay. So with this, we can ignore that we're non-compact in this region. We're also exact, so we have some compactness. Okay, so the definition makes sense. And this R is just that if you have this solution and you push it always on the right in this S, you still have a solution. put hf depending on the function h as the more degrees. So the next question is, how does it depend on h? So if we pick another one, the biggest thing we can do is change the slope. So So if we increase the slope, then we can get the result. If we decrease the slope, I don't think you can get.
So what is K?
Another function. So instead of h, I have another k.
Ah,
H tilde.
okay. Mhm.
So if yeah, you I'm not sure how I should write it, so let me just say it. You take the previous equation, and instead of h, you take hs, which goes from h to k. And instead of j, you maybe take aj base. For these guys, if you have this condition, then you can define the map from the homological one here to the homological one.
From the bigger slope or the smaller slope? Which direction is
Up.
it? Is there geometric reason that that's the direction of the map?
I'm not sure what you're asking.
Well, we just write down how the map is defined.
Yeah.
So my solutions always take input to the left and output to the right. No. It's from, sorry. Yeah. So unless I screw up, you take homotopy from the lower slope to the upper slope. You write the same equation, but with the homotopy in here. And if you're careful, you can, in this case, do it so that you have maximum force.
Are you importing the homotopy is linear at infinity?
I don't know, do I need?
I don't know, I'm asking.
No, I'm not sure. Do we need this?
Might as well.
Sorry?
Use enough. You can do it with that condition.
But do I need it for something? I'm not sure. It might not be good to have two crazy things.
And what happens if you take the homotopy? So if you take the reverse homotopy, do you not get a maximum principle, so you sort of don't get compactness?
Let's see. So I think, yes, you can't choose whatever. That's right. You have to have increasing slope works. So what is it? The equation for this f is something like the left plus 1 order. So I didn't do this for this talk. So can you help me out? What's here? It's F and then ES of. Okay, it's something like this, and this is just good.
Yeah, something like DS of HS or something. Like if you think is what you got. Like you have HS, like your parameter HS,
Yes.
and so it's like del S of HS, which is like the slope. So the point is you want del S of HS to have a sign.
Yeah.
So long as that has a sign at infinity, then you get your maximum principal.
Which is why this goes one way and not the other.
Exactly, exactly. So you can do any homotopy where just del S of HS, like near infinity, has one sign.
That's a great sign.
Has the correct sign.
Correct.
Yeah, has the correct sign.
Okay.
So this sentence is not finished yet, right?
If then solutions, yeah, thanks. Where this stuff is this stuff. Can be used. Okay, so the formula is the same. More questions on this part? So this, whatever it's called, whatever it's called is a chain map. And so we get this induced map. Which is independent of choice as long as we choose the correct guess. Okay. So what is this called? We get a directed. Which is the functions directed by the slope of it. And so we put the limit of the system. That's it, SH. Okay, so there's two examples people always mention. So on the one hand, SH of Cn vanishes. But if you instead take a cotangent bundle, this is supposed to be the module of the free loop space. So Viterbo proved it and other people proved it in other ways. And then the Amiel will talk about some other things, some other ways to compute, about surgery formulas. And then I have a question. Is there some other way to do it? We have these two examples, and surgery, and nothing. Okay.
You mean not using that? Using that as a computation, not using that?
I'm not sure what I mean, but I mean, how do you compute the
The answer
SH?
is, okay, in my talk, at least, you got a way of computing these without ever using the that's true, but never using that group space or anything.
Will you compute this? No.
Yes.
Yeah,
But
okay.
that's the, like, closed manifold and Morse theory.
I'm looking forward to it.
You're gonna compute something, and then, you know, the result is gonna be the same because of this theorem. But you don't ever have to actually compute anything through this theorem.
And this theorem is this theorem? Or
Sorry?
when you say this theorem, you mean this theorem?
Yeah, I mean,
Yeah, okay.
So, I mean, morally speaking, what do we expect SH to count? What is the geometric intuition behind SH?
Well,
If there is one.
I'm not great with this, but the first thing is maybe that the complex is generated by orbits in the interior. So that's like the Morse part.
Yeah.
I'll write that in a second.
And the Morse
And-
part survives.
And
no,
No.
not necessarily. It doesn't.
I don't know.
Yeah.
for Cn.
Yeah.
Okay, it should be one dimensional, you mean?
I mean, the point.
Yeah, yeah, okay. So it doesn't even for C. Okay, good. And also you get the reed chords at the boundary. And because the slope is increasing, you're getting all the orbits of all slope.
Yeah, reboard it's not worth
Yeah, sorry, all lengths. That's a good point. So since we increase the slope, eventually you exhaust the collection of reed orbits. Thanks.
But don't they die? I mean,
Well, the fact that they had to be killed by some, or that something killed them, means that at least they existed. So
Yeah.
it's
you
a
had the
very
Morse,
philosophical
No,
statement.
like you had the Morse minimum of Cn, and it had to kill or be killed by something. It had to cancel with something, and so the something had to be a rate orbit. So then you know there's a rate orbit.
So it doesn't measure the interactions of the dynamics of the boundary with the homogeneous interior.
Yes.
And I think, is it still open that like there is no examples where it's finite but non-zero or something?
It's exact.
So you need to assume it's been a while, for example.
Right.
Yeah, otherwise it has examples, right?
Right.
Yeah.
But then, so then like either if it's infinite or if it's zero, that means it's not the most complex. So you have so
So I drew a special guy, which is more or less mentioned here, that if you have a very small slope and a very small function, so it always comes with a map into the SH. But this is the homology of the X. Since if it's small, you have no reed orbits. Sorry, if it's small slope, you have no reed orbits. If it's small, this is inductive ladder. Okay, what else? Does anyone need the product today? No?
The product?
So there's a product.
you can just say there's
Yeah, there's a product, and it counts such things. Yeah.
Kevin, you don't need this.
I mean, yeah, I mean, yeah, it would be nice.
Okay, so there's a product and it counts these things. And it
Okay.
Make
That's fine.
So I think this is the end. Now we will, I will change the picture a little bit. This goes, and so suppose now you have two Lagrange. You have this is L, this is L prime. they have a bunch of adjectives. The most important are exact. And that's away from a compact region is R times Lagrange.
Sorry,
Yeah.
both Lagrangians are exact, or?
Yes.
Alright.
And we'd like to compute something, some Floer moduli of their intersection. Okay, so we take, we do something to their ends. So we take a h which looks like this, and that's goes away. So we take h which is quadratic in R, sorry, quadratic in R, and we will use it to push one of the L's to generate many intersections at the end. This is
So this x is 2 times a times the revertical.
Yeah. No, sorry, that's the A is not important. Sorry. Thank you. The A is not so important. It's R which is important. So it wraps quicker and quicker. So let me draw something. After wrapping the L prime like it. Yes, thanks for that. We want a complex generated on intersections one with a push of the other, but that's the same as saying of chords starting at one and ending up at the other. Of course. The differential counts strips, which maybe look like this. You go from L and L prime on the other side, and each end is mapped to something.
Can I just say one thing before you? So here, so before you used the linear Hamiltonians and you took a limit to define symplectic homology without Lagrangians. You could also have used the quadratic Hamiltonian then, and here there's also a version with limits, linear Hamiltonians.
you're saying that maybe to be consistent, I should have used one or the other.
Well,
Okay.
you can use either one in either place, but yeah, I don't know. It's just you used one in the first part and you use the other one in this part, but there's no.
So it's a smart way of introducing different ideas.
Also, before you get through this, so just to be clear, you're doing the time one flow under this
Yes.
Hamiltonian, and
Yeah.
that's why it's important that this is increasing as you go to the right, because then you pick up all possible lengths of these.
Yes. So similarly, as you also said about this, previously we had increasing linear slopes, which picked up all the orbits, and now we have quadratic or increasing linear, which picks up all the chords. So this intersection point is a long chord going from L to F, comparing this one.
Sorry, well, since we're fiddling with details, is it important that it's quadratic, or would any sort of monotone with monotone derivative work?
That passes all the slopes eventually.
Yeah,
Super linear, I guess.
at least
Yeah, monotone. Oh, yeah.
Monotone
Well,
quadratic.
yeah.
Yeah.
Or a
it's
limit
okay.
of, oh yeah.
Just as long as it, like, eventually the derivative
You
is
never-
bigger than stays bigger.
Yeah, in two
You
dimensional.
never,
Yeah. Exactly.
you never run into trouble if it's very fast. No. Okay, so what should I say more? Should I say anything? Okay, so the differential, this is a map U, this domain is I times R. Okay, I guess you can change this picture to have a picture from L to the push of L prime at the expense of changing the conjugate with the flow phi. Okay, so put either the Fleur homology of L prime, or maybe the raft of L and L prime as this homology. Is Amel here yet?
The second thing is,
Here.
yeah,
This is just Fleur homology.
Just notation.
Yeah, it is.
okay.
The
And what you were saying is that I can think of this as an intersection Fleur homology of L with phi of L prime.
yes. So there's this part where we don't wrap, or, yeah. And there's this part where we wrap and pick up all the reap chords between the Lechandrians of L, Lechandrian end of L, and the Lechandrian end of L prime. Okay, so I think I should stop. Maybe I should also say some. I think
Stop?
No, so this part stop at least. Or was there more questions or missing information about
What
this
is
part?
it good for?
What is it good for? Yeah, this is the next talk.
Maybe you want to say something about like why the wrapping is necessary for invariance under isotopy, or draw a picture in the cylinder.
Do I know this?
That like if you have infinitely many intersection points and you twisted them a bit versus parallel.
So are you saying if you had something like what? This?
Yeah, okay.
You
so
have to do
that's a-
something.
Mhm.
Yeah. And
The
Yeah.
non-compactly supported isotopies, or?
Yeah, right, so, I guess,
Right.
like, these two parallel Lagrangians, if you, start doing Hamiltonian isotopy, then you could add one intersection point, or you could add two intersection points.
are you saying something like this? Ignore this end. I want whatever I define to be invariant under Hamiltonian isotopy in the compact part.
Yeah, and also maybe in the non-compact part.
So it should also always be extended from some point.
And if you have this kind of infinite wrapping, then
Laura, you can go
Yeah,
on
you
the
can
board.
just-
and-
yeah.
I guess. This is maybe a little imprecise, but if you have this like infinite end, you have this Lagrangian, another copy, if it's like completely wrapped to infinity, then
I see.
if you turn it a little bit, the number of intersections kind of remains infinite.
Definitely.
So,
Yeah, can you make an example? Can you
So
show
if-
where this would fail if you didn't do this?
If
I
this
think it would be
continues
instructive.
like here, and you push the green part, I should say, the green part to the left of the red, you would lose an intersection point.
Yes.
But since we are infinite anyway, it is fine. Is this what you're saying?
Yeah,
Oh.
I think that's.
Yeah, so maybe, yeah, so one comment is that, you know, if you have ends that are different and don't intersect, so your Legendrians are disjoint or something, then you can define everything just not doing any Hamiltonian at all. And then it will be invariant under compactly supported Hamiltonian perturbations of either of these two. Because in that equation that we wrote, the continuation thing, if it's compactly supported, that's kind of, you know, lower order or whatever. But then you still have a problem that, well, first of all, you don't have invariance under non-compactly supported Hamiltonians, even if they're kind of conical at infinity. So this is what Laura was sort of drawing, I think. And the second problem is if your ends are not disjoint, then you don't know. So then what you can do is you can do this infinitesimal wrapping, where you have an ordering on the L1, L prime, so you decide which one you want to push a little bit. So you decide once and for all, I actually don't remember which one, you know, so maybe the first one. You push it a little bit. So now you resolve the issue that the ends are agreeing. So you take a very small slope Hamiltonian, or very little free flow, and then, so that is the infinitesimal wrap category. Because now every object you can just push a little, and then there is no problem. But it will be invariant on the Hamiltonian, compactly supported, you know. But if you want something that's invariant under these conical, non-compact things, then deciding like whether you push a bit or push a bit more, or which one you push first, which one, you know, so this will be an issue. So instead you just do this, and then even the non-compactly supported versions are okay.
Look, there's another philosophical reason to wrap other than just get something that's invariant, which is that you keep track of the rate dynamics of the boundary.
Sure, that's right.
It's just want to have all the rate coordinates.
That's
If you don't
right.
do this, you don't have them. So
Yeah.
Maybe this say, so you can think of Morse theory for real valued functions, and then you can think of Morse theory for complex valued functions, and then you can write the gradient flow equation with the real part of the function, and then you can ask what on earth is the imaginary part doing? Well, the imaginary part is exactly wrapping. You have the open book fiction, that's the monodromy. So if for whatever reason you didn't know any of these, if you just wanted to study complex Morse theory, that would naturally lead you to wrapping for this geometric reason.
So I guess while we're taking over your talk, just
Just a few minutes left.
one sort of completely different point. So there also is a product structure here, and that is the more relevant thing for my talk. So actually, so
Yeah. I can
I don't know if you want to draw
schematically
the
draw
picture.
it. So
You can take a bit longer since we took over yours.
Also, yeah, so the picture is that if you have three guys, I don't know, let's just draw them like this. You want to have a disk or something of this type going in here, where this is L prime, this is maybe L prime. Something. Okay. If I want to write some formulas, I guess I should be careful because what's the reason? So a priori, I should not. How does this work with wrapping? A priori, allowing something like CF, whichever ones, with 2H, right? So I have to use this one. Yeah. But, okay.
So yeah, this is if you're doing the wrapping sort of in this linear way and then taking a limit.
You have all
Yes,
this.
so you have like your first chord from like, you know, from L to L prime, you know, if you're doing this in the linear way, like whatever slope you took there, and then whatever slope you took between L prime and L double prime, like the chord that you get on the right side is sort of like a combination of those two things.
Yeah. But that actually makes the limit version better. Because
Yeah.
then you're okay. And then if you have the quadratic one, you have to do some kind of rescaling.
Exactly.
To get back to the original quadratic.
Yeah.
So you can do either again.
Yeah.
So it's the quadratic version will have to have this extra ingredient.
Yes.
Which is why he was writing 2H there.
Yeah, yeah, I see.
Okay, can you write down, so you get a map from a tensor product of something,
You want me to write the?
just schematically, yeah.
See,
Yeah. So this is where?
One of those needs to be,
Did I switch order somewhere?
You have from L double prime to L prime, and then from L prime to L, right? So it should go from L double prime to L.
Is that consistent with the picture? I'm not sure.
It depends on your convention.
Okay, this is what you wanted?
Yeah.
Okay. Do you also want me to put more stuff in here?
This sounds, this is,
Okay. N dot N. Looks like this. And you have more stuff in here.
Oh, it's true, your title said wrapped Fukaya, right?
Yes,
Yeah, okay.
I guess. Yeah, so your products should, I mean, schematically they look like this. They have several more punctures, and each component of the boundary should map to one of them. Now for something completely different. I promised Damian I'll draw this, if you have, I'll redraw that picture, but this way. If you have Y, here's X. This is Legendre, and sphere. So this is N minus 1. You want to do surgery along this, and I'll just draw. So, make good. This the blue is a neighborhood of lambda in Y, which you may think of as there's a J1 lambda over lambda, and you take a disk in that. and we've seen this. This is a disk of the cotinate disk of the boundary. And we've seen this map many times, I think. Okay, so if we want to fill in this, there's a sphere at the boundary and we want to fill it in. So I draw some result. Yes. Okay, so I think I have first picture I wanted. So we used to have a vector field out of y, and in the neighborhood of lambda, it now looks something like this. So let me redraw it yet again. Yeah, okay, so I think that's it. And this is the starting point for the next talk about this C, how it plays with its boundary. I don't know what lambda C maybe. Yeah.
So the red guy is core and the blue guy is
Co-core.
core of the handle, I guess.
Maybe the word handle and surgery should show up.
Okay, yeah, so you want the serger along this sphere, and the handle is drawn here, and now it's Good.
Okay, but y tilde is the result of surgery
Yes.
on y by lambda, Legendre surgery, and yeah. The new Weinstein manifold is the result of handle attachment on x along lambda.
X tilde, yes.
Can you maybe draw a picture of what lambda looks like, in a surgery representation? Let's say that you take D4. You take a Legendre knot in D4.
I want this.
This maybe relates to what Vilas was looking for. Vilas will show you.
What are you asking?
The Legendre lambda C should be the meridian of the knot, right?
That's true.
I don't know if it's meaningful to anyone, but or if it's useful in any way.
Maybe.
I mean, I think the point is that this co-core links intersects transversely with the core. And if you isotope the boundary of the co-core along the handle down towards Y,
Yeah.
then it comes out as a meridian of the attaching Legendre.
Yep.
And sometimes that's a useful perspective to have. You can also push it in other ways so that it comes out as a push-off, a Legendrian push-off. So you have some flexibility about pushing things around into the handle and then back out.
The push-up would be either the first one, you can just slide the negative to the center.
I'm still.
I like this. It's to be continued. It's a cliffhanger.
So you have to come back at 11 for our talk to hear part 2 of the story.